Piotr Sulkowski from Warsaw, who will tell us about BPS states, knots, and quivers.
Thank you very much for the invitation and the chance to speak. So that's indeed the title of my talk. Let me say that this is the work which is being done or, well, partly completed, but hopefully it will be generalized as well. It's done with Piotr Sulkowski, whom you already know, Marko Stosis, who is also with us, so I'm like counting for your help, and also Markus Reinecke. And you can probably assign these names to the part of the title. So of course Marko is an expert on knot theory, which we are happy to work with. Markus Reinecke works on queer representation theory among other things, so he's like responsible for the last piece. And me and Piotr, let's say we are responsible for, let's say, physical interpretation and physical input. And as you see, much of what I will present, in fact, will be somehow calculational, which is also kind of more physics than mathematics philosophy, but we hope to inspire you, and clearly, well, we very much believe that there are big conceptual issues behind the picture. So the main claim, or let's say that's a conjecture, something I like to convince you about, is that information about knots and their invariants is encoded in quivers, and more precisely moduli spaces of their representations. And that's quite a general statement, so I'd like to, well, list some places where, list some manifestations of that. Before I do that, as an appetizer, let me just make a picture. Okay, so that's one part of the picture, which is of course well-known trefoil knot. But the other part of the picture is this quiver, which appears in the title. And essentially one of our results is how this picture looks like. So as I just said, much information about this knot and its invariant, it's encoded in this quiver, and more precisely moduli spaces of representations, but even just in a picture. So what are these various properties and invariants that you can match? For example, the obvious thing, the first thing which you do when you draw a quiver are vertices. And on this knot theory side, they correspond to generators of HOMFLY homology. Then, when you draw the picture, after you draw vertices, you draw those arrows. Oh, I forgot one important issue. There can be also loops, and that's very important. Here we have some loops at some of the vertices. So in a quiver you have arrows.
Question. Is that an accurate representation of the quiver associated to the trefoil?
Yes.
Okay.
Now it is accurate with those loops. That's important. So in fact, if you are somehow familiar, let's say, with HOMFLY homology, you can already start trying to identify some features of this picture which are familiar on the knot side. And one aim of my talk is at the end to, in fact, derive why this quiver looks like this. So maybe I should even start with a kind of clarification that the way we derive this quiver is not very straightforward. We can get it, but somehow in a roundabout way. So one big problem we are facing is how to find this quiver faster. So that's why I need the whole talk to present this quiver, but if you would have a faster way, maybe I could use 10 minutes and that would be fine. But I don't know that, so let me continue. So those arrows and loops correspond to, for example, framing, and also some of the homological degrees of these generators. I will be more specific later. Okay, so these are very crude things, but then something maybe more interesting is that colored HOMFLY, let me be more accurate, HOMFLY PT polynomials correspond to something which is called on this side motivic, or they are encoded in motivic generating series. And in fact, when we started the work, our main focus and motivation were just colored HOMFLY polynomials. We didn't, to start with, think that much about this HOMFLY homology, but it somehow came out from the picture. So it is like, as you will see, this is encoded in those colored HOMFLY polynomials.
If I just gave you the HOMFLY homology of a knot, can you construct everything to do with the quiver? Did you need the knot, or did you just need it?
In fact, I don't need a knot. What I need at this moment is I need colored HOMFLY polynomials in symmetric representations. So, of course, if you know the knot, you are able to compute them in this or the other way. But, okay, and so one motivation was just polynomials, but then we saw that those homological information somehow arises, and we had another motivation which was somehow crucial as well, which was to understand what are those Ooguri-Vafa or Labastida-Marino-Ooguri-Vafa invariants, which were presented in the talk by Piotr and also Ramadevi. And as you know, they are, or they, well, at least in general, they have not been like rigorously defined, but what we find kind of surprisingly that these invariants can be related and can be expressed by motivic Donaldson Thomas invariants of the corresponding quiver, which on one hand you might use it to define them rigorously if you indeed believe in this correspondence, but what is even more important is that these invariants are proven to be integer by people like Reinecke and others, and we express this LMOV invariance as some maybe combinations of these Donaldson-Thomas invariants with positive coefficients, which immediately proves that these are also integer. So at least if we are able to find a quiver for a given knot, then we immediately know that all corresponding LMOV invariants in symmetric representations are integer. And we believe this holds for all knots. Well, we don't have a proof in general, but I will also present many examples that we dealt with later on. And then there are various other features which one could think of. For example, for many years it has been postulated that if you have well, this type of a system which can be engineered using some brains in string theory and so on, then you can associate to that so-called algebra of BPS states. And in fact, rigorous formulation of this algebra was a motivation for Kontsevich and Feubelman when they introduced well, this series of works on wall crossing and so on. In particular, they introduced something which is called cohomological whole algebra, which they associated in particular to a quiver, which was supposed to be a realization of this algebra of BPS states. So we think that indeed in this case this is what we are interested in. And if you have a quiver, we can of course immediately identify how this algebra looks like. And finally, well, I will also discuss in more details, but these objects on this side, in particular, the LMOV invariants, they appear as some Betty numbers or dimensions of these moduli spaces of quivers. So in that sense, you might think of associating these quiver moduli spaces as some kind of categorification, where you have some more general objects, you compute some dimensions, and then you reproduce like numerical invariants. So that's general idea, and I will spend a little time on presenting some objects from this left-hand side and then from the right-hand side, and then at the end I will try to connect them and show how it works in detail. And I'm quite, well, happy that already some talks covered some of these topics, so I don't have to present them in that much detail. So let me just, well, say very briefly that we may think of colored HOMFLY polynomials. I will denote them like this, where R denotes relevant representation as expectation values in Chern-Simon's theory. With usual identification of parameters, if we think of SUN Chern-Simons at level K. And one, well, so in this community that's obvious, one long-standing puzzle was why the coefficients of these colored polynomials are integer, and the solution are, of course, the homologies standing behind that. What I am, well, interested in is triply graded colored HOMFLY homology. I am aware that this is not defined as rigorously as many of you would wish, but at least there are some ideas how this homology should look like. I'm not going to go into details, but just as an example, let me write the super polynomial, or this is called colored super polynomial that we expect to exist. Let me just write it to have some example that we would like to converge to for trefoil knot. This is how it looks like. So of course our coefficients are positive because here we take dimensions and with some monomial which has this positive sign. And this, in particular, are some of the homological degrees which correspond to these loops here. By them I mean the powers of this t which appears in this expression. So these are 0, 2, and 3 in this case. And then if you take t to -1, you get just HOMFLY, ordinary HOMFLY polynomial. So these are just a few words about those super polynomials. Let me also well, just recall and maybe introduce my notation, a few words about LMOV invariants. So as Piotr and Rama presented, they can be identified after you write the following series, like kind of generating series of colored HOMFLY polynomials, where this PR with bar denotes unreduced colored HOMFLY, which means that we take the colored HOMFLY I mentioned before and then multiply it by some factor which corresponds to the unknot.
We want to put a bar.
Yeah, that's right.
And with a bar.
Okay. So general claim is that it can be written like this. I mean, this is this claim by Ooguri and Vafa. And then the LMOV invariants are encoded in those functions fr. And they have some physical interpretation as counting the numbers of those BPS states which arise from D2 or M2 branes ending on M5 branes. This is the picture that Piotr presented. What we do, this is kind of an important step, is that we consider just symmetric representations, which we can practically do by taking this source to be just one-dimensional. In general, this can be matrix of any size. We take it to be just some generating parameter x. So in that case, just this expression reduces. In what follows, I will probably often denote it then just as a p of x. Then this is a sum just over integers which label symmetric representations. And then, so this trace in representation R is non-zero only for symmetric representations. It's non-zero only if, or so in other words, for V being one-dimensional, this trace is non-zero only for symmetric representations and takes the following form. So that's left-hand side of the equation. Right-hand side, you can work with this product a bit and write it in the product form, which then looks as follows. And then I will denote the LMOV invariants just by n with index r, ij. They appear in this power, so just the question is why are they the integer, and well, of course, what do they mean also mathematically. So I will focus more or less on this class of those invariants. And also, just an example, I will need that at the end. Let me just write how they look like, because at least for some knots, one can write general formulas for those colored HOMFLY polynomials, and even one can write general formula for colored super polynomials. So this is what I will take advantage of. So in case of trefoil, such a formula takes the following form. And then here is essentially a Kupoch hammer symbol, which I will write explicitly. And if you set t to be -1, then you get this expression. Then you can try to, at least this generating series, then you can try to factorize it and read off what are those ends. And let me stress that there was a lot of activity, especially after the Ooguri-Vafa original conjecture almost 20 years ago, where people tested that conjecture, working out what these numbers are, but what they had available were just values of colored HOMFLY at several representations labeled by some small Young diagrams, because that was all that was available or was possible to compute even on computers. So somehow our idea, or well, philosophy is to be able to say something about these invariants more generally, not just looking at purely at examples. So of course, when we have this expression, we can put it on computer, regroup it, write in a product form, and one by one read this, and we can go as far as our computer enables us, as far as we have patience, but we want to say something about all our, not just a few of those. And well, of course, if you set R to be 1, which means you look at fundamental representation, then I get this answer that I already wrote before. It was a square over q square and those three terms. So this is more or less what I will need regarding those colored HOMFLY. So let me just now say a few words about this other side of the story, namely quivers. So we had several motivations to look at those quivers. One is that, like, physically you might expect, if you have this physical setup with brains and so on, you can somehow reduce it dimensionally to, in fact, just a quantum mechanics, and you can consider something like word line of quantum mechanical particles, which in general might be governed by, in fact, quiver quantum mechanics. So the question might be, can one identify this quantum mechanics?
Sorry, can you say again what the vector space V was?
I just take it to be a single parameter, like generating parameter x. In general, V might be matrix of arbitrary size, in principle of infinite size if you consider large n.
But it has nothing to do with the representation, the color. I mean,
no, I was just computing a trace of, in the representation R, of, well, then I need to have appropriate V. But usually people consider V to be like of infinite size to capture all possible Young diagrams, all possible representations. But I'm focusing just on symmetric representations, which I can do by taking V to be 1 by 1, and that's what I do. I do this for two reasons. One reason is that things are more manageable then. But another, maybe even more important, is that what is known on the quiver side corresponds precisely to this case of symmetric representations. So I will mention that at the end. But one of the questions we face now is how to generalize the quiver side to what, like, knot theory suggests. Okay, so I will also be very brief when I talk about quivers. I mean drawing a picture like this one, where I have some vertices or nodes, which maybe if I use some notation, I will call them by I, and this set of vertices is called, let's say, Q0, and I have some arrows, Q1, and I have C in general, Cij arrows from vertex I to vertex J. So in particular, the information about the quiver can be encoded in this matrix C. And, well, so physicists think of quivers from one perspective, mathematicians, of course, from another perspective. Usually, when one considers quivers, one specifies so-called dimension vector. Which is a set of positive integers or non-negative integers, which are assigned to each vertex, and for physicists they denote the gauge group of the associated system. So this is just a product, typically, of U di gauge groups. And then for physicists, arrows represent some matter fields which transform in representations. Well, they transform under two of those U d gauge groups, and the arrow shows according to which of those gauge groups they transform. And of course, mathematicians have slightly different views. So typically, you assign some vector space to a given vertex. Of course, it can be much more general, but for my purposes, let's say this is just c to power di. And then Baij are linear maps between those complex vector spaces. So then the question is, what is the moduli space of representations of this quiver? So for physicists, this moduli space is like a space of ground states of the system. For mathematicians, this is just a space of all of these maps which satisfy certain conditions. So let's say that a representation is a set of those maps from CDI to CDJ, such that, first of all, more generally, you may have also some potential, which is called a superpotential by physicists, assigned to a quiver. So you want to minimize this potential, and then you would like these representations to satisfy some stability condition, which, well, I will not discuss in detail. If you know what pi Stelbin means, then the moduli spaces I'm interested in just use this condition. You have mod out in this case everything by the product of GL BIC groups.
Is W fixed, or is it a part of?
In fact, in general, it is fixed. But in fact, in our story, W doesn't play a role, and this is 0. So mathematicians would like to analyze these representations and tell everything you can about them, what are like their cohomologies, dimensions, and so on. In particular, these Donaldson-Thomas invariants are related to like Betty numbers or cohomologies of those moduli spaces. But in general, this theory, well, the theory itself is developed, but explicit results are not known in many cases. They are known for some classes of quivers, and apparently one of these classes is precisely what we need in our setup. So this class is the class of quivers which are symmetric. which means that if you have an arrow from I to j, then you also have an arrow from j to I, which means that this matrix C, which defines the quiver, is symmetric. And thus this potential is 0. In that case, it is proven, well, it is known how to extract these Donaldson-Thomas invariants, and this is even proven. It was first conjectured by Koncewicz and Soibelman in one of their papers, and then it was proven by Efimov that it is motivic dt invariants are not only integer but positive integer. So this is known much more about this case, and let me tell you how to get this invariance. So what is now kind of interesting is that you shouldn't analyze each of those cases separately. I mean, you shouldn't specify a dimension vector and look at a given moduli space, but this is much more efficient to look at all of them at once. And it is known that these motivic Donaldson-Thomas invariants are encoded in motivic generating series, which is essentially a generating series of dimensions of certain cohomology spaces of for that moduli space. And this motivic generating series looks like this. So you assign several generating parameters from x1 to xm to each of the vertices, and then you consider all those dimensions vector at once. And as you see, this matrix representing the quiver now plays a role in this expression I am writing. Times, and here I have a ratio. This looks just like this. And the way this Donaldson-Thomas invariants are encoded in this series is such that now there is a statement. This is what follows from these works of Koncewicz, Soibelman, Efimov, Reinecke, and others. The statement is that you would like to factorize this series, which apparently looks very analogous to what we did with LMOV invariants. And then this omega dk here in those exponents are those motivic Donaldson-Thomas invariants, which I meant here, and which are proven to be integer, even positive integers in that case.
Should there be something in the upper right-hand side of the board, that formula, how does it depend on the quiver you started with? Is it only
of course. So just through the C's, they tell you, if you know C, you know this formula, essentially. So, of course, when you look at this generating series, at first sight, it doesn't look that much, well, maybe a little, but It has some features of this formula, for example, but it's not immediate.
The formula has nothing to do with the moduli space, only on those C's.
This formula, I mean, it has to do because this, if you now factorize it, then you get these omegas, which are those Betty numbers for those moduli spaces of a quiver. But the issue is that you have to write it down for all representations, then factorize, and then if you pick up this omega with particular d you are interested in, you get information about a given moduli space. So when you look at this, well, maybe it has some similar feature to this, but there are many Q-series, of course, in the world, which some of them have nice properties and some of them have bad properties, and not every two Q-series are identical. But this product, the composition looks practically the same. There is just one difference. Here we have several xj's, and in that not theory side we had just a single x. But of course, this is something we can deal with. If we have too many parameters, we can always specialize them. So now our main statement is just this, that if you specialize those x's in an appropriate way, then this generating series, which we get from not theory side, you can make it identical for generating series associated to some quiver. And if you do that, you can identify what the quiver is. So again, this is, well, let's say our conjecture is that it should hold for all knots, and even if not for all, then for very large class. I will show you later some examples. So this LMOV generating series can be identified with Motivic generating series or some quiver under some specializations, which let me first write them roughly. So roughly they look like you just take xi to be single x, and then you possibly multiply it by a and q and minus 1 to some powers which are linear in those di's. So that's roughly, you have to play a bit with that formula, so I will just write the final result now.
Sorry, Piotr, probably you just answered this question. What's the significance of k in omega d k?
No, I didn't answer this question yet, but this k, this is just a label for fixed, let's say for fixed d, there is a finite number of these omegas which are non-zero, which are labeled by k. So this is just like in LMOV invariants. For fixed representation, you have a finite number of...
But I understand ij. What's the meaning of k here? Is it like...
well, they select some of these homologies you are after. So just details about the whole moduli space, but then you want to focus on some homology classes also. Okay, so I will just rewrite this generating function, but taking relevant identifications and relating the expression to knots. And I will write it in the form which now encodes the information about the knot. So denominator, well, is the same. It's just a bunch of those Q hammers. There are m of them. And here let me write it in the following form: x to power d1 plus dn, and then product I from 1 to n, q to power qi. I will explain in a moment what these are. Ti di, a to power ai di, and I'm sorry for that. I need, okay. I need also minus 1 to power t I d I. So again, this Cij is a matrix, some symmetric matrix in general, which we claim corresponds to some quiver. X is raised to the power, which is just the sum of the i's. So if you are writing this generating series of LMOV invariants, it was just of this form. Here was a sum over all symmetric representations. So x to some power r on this side arises from those x's which are raised to the sum of these, which just gives this given r. And then here we have a, q, and minus 1 raised to some linear powers in these, and the coefficients are ai, qi, and ti, which are homological degrees of these generators, which I mentioned in the very beginning. So maybe let me come back again to this example of trefoil. That was the formula. So I mean that, well, these homologies are in one-to-one correspondence with monomials in the super polynomial, and each monomial is of the form, it is a to some power, which I'll call ai, q to some power, which I'll call qi, and t to some power, which I call ti. So then you essentially, for a given d with some index I, you use those degrees and plug them here. This is a conjecture that it can be written like this, but this is, as I say, what we see in many examples, including some infinite families and so on. So I try to convince you that it works indeed just in this trefoil example, and make a short computation, which is really just one-line or two-line computation. And basically you have to use one identity, which, if only you know that what you are looking for, at least in this case, this is quite obvious. Let me just write the full generating function from r0 to infinity. Then I have x to power r, and then I want, here is one subtlety, I use some non-trivial normalization. It's like part of the unknown normalization. I can, well, discuss that later, but I don't want to go on a sidetrack now. I just take this QQR QPOH hammer, which is in the denominator of the unknown colored HOMFLY. For a moment, I don't take the numerator. So the same here, I sum over r, x to power r, and I also include this factor. And so as I mentioned, this product is in fact QPOH hammer, and I just use one formula for a QPOH hammer, which is a Q deformation of ordinary binomial formula. If you have such a QPOH hammer, you can write it as a sum of Q binomials like this. So this is what I do here. I identify this z with this a square and q and t in some power. Well, in fact, let me just specialize to HOMFLY at this moment. So I don't want to consider super polynomials, so I just erase t dependence. And it should have been plus here, but when I put t minus 1, then I get minus. So instead of this Q-Poch hammer, I just use this formula. For a moment, let me not look at these monomial factors, but just at the factors which arise from those Q binomials. So Q binomial is, of course, R over K is like Q square R, Q square K, and Q square R minus K. So this numerator here, which appear here, will cancel with this one. And here will be the same numerator with K, which will cancel with this denominator. So at the end, I will be left just with a formula which is a sum over R, K, and I, which has some, well, x to power R, and then Q to some power minus 1 to some power. And in the denominator, I have Q square R minus K from this first Q binomial, Q square K minus I, Q square I. And now I just call I to be D3, K to be D2 plus D3, and R to be D1 plus D2 plus D3, so that you see that this 3 Q-Poch hammers become just Poch hammers with D1, D2, and D3, and this is precisely the form which I am expected to get on the right hand, I mean to get from this expression. Then if I play a little and then adjust these powers of Q, I find that this C is of the following form. Which is the matrix precisely for this quiver I had in the beginning. And in particular, you see that on the diagonal of this matrix, you have those t degrees, namely 3, 2, and, well, this is t to power 0, which are therefore the number of loops at each vertex, because if something is on a diagonal, it means the number of arrows from vertex I to vertex I. So that's the number of loops. And if you look carefully, of course, you will see that what you get agrees with this general claim that we have. So let me stress that once I did this rewriting, I just, well, it took me a few minutes maybe to more for this talk, but I just used this one formula for Q-Poch hammer. And doing that automatically proves that ln of v invariants are integer for all symmetric representations for the ambit. Because after I did this rewriting, I know that there is, well, this formula matches this with some specialization, so I know that on this motivic quiver side you can factorize that from some general theory.
If you had a trefoil mirror, it will just change? The mirror will just change?
Well, it's
Loops 2 and 3 will get interchanged?
they change somehow. I cannot write immediately.
They change in a well-defined, well-controlled way.
Okay, so we agree. Yeah,
It is trying to put like a mirror there and see.
you have to work a little.
Figure 8 may be symmetric is what it.
You have to play a little, but that's not hard to work this out. So let me end with some comments and also let me mention some other cases that we worked out. So, as I stressed, we don't have general proof, but we have a lot of evidence. And the minimal thing this evidence does, it proves integrality of this LMOV invariance for all symmetric representations for a bunch of knots we have looked at. So some more examples that we did. Some of them are more obvious, maybe some of them are a little less obvious. So first of all, we looked at 2 to p plus 1 torus knots. Well, even 2p, let me write, 2p torus knots and links in case when we color all components by the same representation, as well as all twist knots. And what is nice here is that if you have this infinite class, you also label twist knots by some integer, that we can consider the limit when p goes to infinity, and it makes sense on the quiver side as well. So there is some like infinitely large quiver, and those people in quiver representation theory also consider such limits, and somehow it makes sense here. So that's one nice feature for those examples. Then we looked at 3 p torus knots. Well, not for general p, but several of the lower p's like 4, 5, or 7. We see some features which we think will help us to do that for any other p. But here is one important issue, that once we believe that this would be the correct structure, even if we don't know expressions for colored HOMFLY, we can at least conjecture them or derive them. If we know that we should get this color HOMFLY should be assembled into this form, then we can see what matrix Cij gives at least known colored invariants for as many colors as we like, and we indeed did that. It matches as high as we can go, and then we have general formula for any color. And we essentially have the results for all knots up to and including 6 crossings. And for example, for 6,2, we get a quiver which has 11 vertices and matrices of size 11 by 11. For 6,3, this is 13 by 13, so they are quite large. So this seems to be quite non-trivial check. And in particular for 6,3 also there was not known, I'm not sure about 6,2, but general formulas were not known before for any colored representations. Now we have them. So these are some of examples. We also see many other nice features. For example, in the very beginning I mentioned framing, which we know what does on the knot side. If you have some integer framing f, you multiply a given colored polynomial by a factor which includes q to power f. For symmetric representations, this is just r minus 1 times r and then times f. But as so the quadratic term which arises from here, qfr square, as I mentioned before, r is just a sum of all those d's. So when you change framing, you include such additional factor in the generating series, which means that the matrix C changes by like a matrix which is just matrix of units. So a change of framing on the knot theory side corresponds just to shifting the matrix C and adding f loops and f additional arrows between all pairs of vertices. And what we also see, this is kind of implicit, and also what I meant before, we can start just with colored HOMFLY polynomial like this. We write it in this form, and then we identify matrix C, so we know what the quiver is, but in particular we know what are those t degrees. So in this way, if we know all this colored HOMFLY, then we automatically know colored superpolynomial, at least in the fundamental representation, which doesn't seem to be obvious. So to conclude, let me just write down a few let's say, hints which come from not theory side, that could be some inspiration for quiver representation theory, or the other way around, something that comes from quivers and suggests that something like that should work for nodes. So, well, the first issue is, of course, one of the main motivations is this proof of integrality of LMOV. So we somehow think or believe that this could be some general approach which might help prove this LMOV conjecture in general. Those quiver provide something we would call refined counting of invariants. Namely, once we know the quiver, we can write this generating function for the quiver, and it depends on those x1s and xm's, and they are corresponding invariants, which we can also write down in case of nodes. So we could think of something like refined HOMFLY or LMOV invariants, and we can write them down at least in all these examples that we thought of. And then there are also some combinatorial constructions associated to quivers, in particular the one that Piotr mentioned in his talk. So it suggests that you could use this combinatorics to understand also properties of these things that you are supposed to count on not theory side. And then the question is, why do we see just these quivers? Well, some specific quivers. Of course, it's not that for each symmetric quiver that you write down, there is not a corresponding knot. So the question is, why do we see some specific quivers? And moreover, it seems that those specific ones which we just focus on, they do have some special properties which are not the properties of all quivers. So this is a bit puzzling. So let's say these are some hints from quivers and from nodes. We know that this is very natural to consider more general representations, not just symmetric ones. So the question is, can you get results for all representations, also from this quiver, or maybe some generalization of such a quiver? But like not theory input suggests it should be somehow possible. On not theory side, we have various recursion relations. A polynomials and A hat polynomials and so on, which have to do just with these relations between symmetrically colored polynomials or superpolynomials. So it suggests they should also play some role on this quiver side. And of course, in not theory, we have many other formulations which could also be maybe related to quivers. So I think that's all. Thank you.
Is there any kind of meaning for these x variables?
Those x's?
Yeah, I mean, do you get other well-known invariants by specializing them differently, or?
Not at this moment. We get more invariants, but we don't quite have like not interpretation what they mean. We have, so in this combinatorics context, we have some combinatorial interpretations, then we see what they should correspond to, but it's not like some intrinsic not property that we can state it. at the moment.
And the number of them, the number of these x variables is the number of vertices in the quiver?
Yes, which is the same as number of this HOMFLY homology generators, number of monomials in super polynomial.
Is there any sort of, not homology interpretation of the off-diagonal elements of the matrix C? I mean, what are those?
You mean not theory?
I mean, yeah. Like, so you could find the on-diagonal element.
Well, we can say something about the first row, for example. So if you look at various degrees of the fundamental HOMFLY homology, then some differences or so correspond to the first row, something like that. But we don't have general picture for all of the matrix.
Can you say what the matrix is for the 2p torus knots?
You are asking what is this for 2p?
Yeah.
Well, I don't remember it by heart. I can show you that. I mean, you have it written down, but it is like it grows. I mean, it grows linearly with p, of course, and roughly each entry also grows linearly with p. Oh no, sorry, it's not growing linearly with p. The entries which were present for smaller p's stay the same. So I erased that. Well, when you increase speed and you add more rows, and then you have more entries, but those which were before stay the same. So this is why this limit is possible to take, the one on the top of the blackboard. So you just add more vertices and arrows between these vertices, but the structure you had for other nodes with smaller p stays the same.
So from such a quiver, can you recover the generating series for the non-great polynomials of the color tricky graded homology?
In fact, yes. So I didn't mention that, but I erased general formulas. But so in this general formula, we had A, Q, and T. We know how to replace them by, we can even do quadruply graded.
If this is true, does this imply a strict exponential growth property?
Well, you can certainly you can see this form why this should be so if you have exponential growth property. But does it imply in the other direction? I'm not sure.
Yeah, so maybe if you're very strict, then that implies exponential growth property. These linear terms are coming from exponential growth. So for those knots, it is definitely as Piotr was explaining, but you should be a little bit more.
Would you expect a quiver description for knots that have somehow faster than this strict exponential growth?
Well, I can expect, but
if you produce a formula.
Maybe, I mean, of course, there are more quivers, so even if some knots behave strangely, maybe they are not in this class of symmetric quivers or whatever, I can say that.
What happens if you mutate this quiver or do a Seiberg duality or mutation on this quiver? Does it still correspond to the same knot?
For these quivers, we don't have mutations, in fact, for symmetric ones.
Oh.
It's not possible to mutate.
All right. Let's thank Piotr again.